This video is about integrating with polar coordinates. And as I mentioned before, we'll be working soon with both cylindrical and spherical coordinates. So if you haven't learned polar coordinates really well before this, now is the time to do it, and I will help you. So you did see this in Math 126, but depending on where you were, as far as workload, maybe you didn't pay as close attention to it as you could have. So what are polar coordinates for? Well, some double integral problems can be solved just by integrating the way it's easy to set up. Some of them you need to switch the order of integration with Fubini's theorem, like we saw in the last video. And then some of them, such as this problem here, neither of those things will help, and you need polar coordinates. And it doesn't solve everything still, but we can solve more problems if we have more tools. So we have a region bounded by x equals the root of 4 minus y squared in the y-axis, and we're integrating this lovely function e to the negative x squared minus y squared. So how do we do this? Well, first we got to figure out what the region is. So if we square both sides of this first equation, we get, and add y squared to both sides, we get x squared plus y squared equals 4. So that's a circle. Actually, this thing up here is a semicircle, and that's because x is the radical of something, so x is greater than or equal to 0. Radical takes non-negative square root. So if we draw this, we have a circle of radius 2, because 2 squared is 4, and we only need the part where x is greater than or equal to 0. So that's over here. And then we have the y-axis here, so we're integrating over this semicircle. Okay, so if we just set this up with Cartesian coordinates, what's the easiest way? We want y to go from 0 to 2, and then we're going to take horizontal lines like this. So we're going to go, y goes from negative 2 to 2. I don't know why I said 0 to 2. Negative 2 to 2, dy on the outside. And then for each value of y, x starts at 0 and goes to this curve, which is the root of 4 minus y squared. So e to the negative x squared minus y squared dx. So that's difficult to integrate. We have an e to the negative x squared. Same thing, last time we had an e to the positive y squared. That was difficult to integrate too. So maybe we can fix it by switching the order. That worked last time. So how would we do that? We would integrate vertical lines now. So now x is going to go from 0 to 2. Put dx on the outside. And then for every value of x, y starts at, we start and end on the same curve, except we don't. These are two different curves. So same thing happens if we try to isolate y here. Then this curve is actually y equals negative root of 4 minus x squared, and then this other curve is y equals positive root of 4 minus x squared. Because remember, the radical takes the non-negative square root. So if we take this part, we get the top half of the circle. And you can get this other part too, but we don't want that. And so we need to put a negative sign in order to get the bottom half of the circle. So we're actually going from negative root 4 minus x squared to positive root 4 minus x squared. And then same function. And of course, because the function was symmetric in x and y, changing the order of integration didn't help. This is still really hard to integrate. It's still e to the negative y squared. Okay, so bad news. We need a different approach. We need polar coordinates. And remember, the conversions for polar coordinates are r equals x squared plus y squared. And then we have r cosine theta equals x and r sine theta equals y. And we can get that just from the unit circle, right? We have a point on the unit circle with angle theta. This should have been how sine and cosine were defined for you. They may not have been. You might have done it with triangles, but this is the better definition. A point on the unit circle, angle theta with positive x-axis. The point is cosine theta sine theta. And if we stretch that out to a circle of radius r, then that point is now r cosine theta, so radius r instead of radius 1. R cosine theta, r sine theta. Okay, and then what do? Well, we make polar graphing paper. So remember before, when we were integrating, we were cutting the whole plane up into little tiny rectangles, and then we had rectangles with width dx and length dy. that's how we got the dA equals dx dy, and that's how dx dy ended up at the end of our integral. Okay, so what's dA now? Well, we're going to chop up the plane in a different way. We're going to make a bunch of circles and a bunch of radial lines. Right? That's how we change r and theta. Changing theta moves us to a different radial line. I don't know what I was trying to draw there. That was weird. Changing r moves us to a different circle. So what are we going to do? We're going to take this polar rectangle, basically, here. And then what is that? Well, that's almost a rectangle. So it's really that width of the slice dr multiplied by, and then we're going to get this arc length thing. Okay, so that's kind of weird, because on the unit circle down here, the arc length, the change in arc length is d theta. So down here, we have d theta. But then as we stretch it out to a circle of radius r, same thing as with the coordinates, the arc length stretches. So the arc length is now r d theta. So in polar coordinates, dA is not dr d theta, it's r d theta dr, or people write it r dr d theta so that we can have all the same variables together. But the r d theta comes from the arc length, and the dr comes from the width of the little polar rectangular slice. Okay, so that's everything we need to know about polar coordinates. Now we can do this. So we're going to replace dA with r dr d theta. We're going to replace negative x squared minus y squared is going to be negative r squared using that. So we get e to the minus r squared, r dr d theta, and then we have to look at our region again. So what's happening? Well, r is going from 0 to 2, so that's going this way, right? R starts at 0 and ends at 2. And then theta starts at negative pi over 2 and ends at positive pi over 2. We go all the way up to the top of the semicircle. And now this magic thing happened. This weird r actually helps us integrate, because now we have a u substitution. So u equals r squared, du is 2r dr. So r dr is 1/2 du. This looks a lot like the problem in the previous video. So then that equals negative pi over 2 to pi over 2 integral. I'm going to keep this as r equals 0 to r equals 2. This is e to the negative u, and then we have a 1/2 du d theta. Integrate that. It's a little bit tougher than last time. We get a negative sign, so negative 1/2 e to the negative u. And then I'll go ahead and replace u with r squared here. You can do this in one step if it's easy. And then r goes from 0 to 2. And later I'll still have to integrate with respect to theta. All right, so negative pi over 2 to pi over 2. I put in r equals 2, so it's negative 1/2 e to the negative 4. Minus a negative, so that's plus 1/2 e to the 0 is 1. Okay, and that's all integrated with respect to theta. There's no thetas here, that's a constant, so I just end up with that ugly constant times theta, and theta goes from negative pi over 2 to pi over 2. So I plug that in, I get pi over 2 minus negative pi over 2 is actually positive pi. So I'm going to, I'll take out the 1/2 in front too. So maybe I'll take out negative pi over 2, and then it'll be e to the 4 minus 1. All right, so polar coordinates can help us solve problems that were impossible with Cartesian coordinates when we tried them. If you know it's going to be polar, you don't have to try Cartesian first. But that's what they're good for.